This is an introduction to World War II aerial gunnery and the K3 computing bomb sight. Before showing the bomb sight, I'd like to clear up a few terms that we'll be using during the discussion. The first is deflection. Deflection is the number of degrees that you have to aim off of the target to account for the relative direction and speed of the gun platform as well as the target. We're all fairly familiar with the idea of leading a target when you are stationary and the target is moving across your field of vision. But depending upon the relative motion of the bomber or gun platform and the target, it may actually be necessary to aim behind the target, above the target, or below the target. Another term is point blank, and in military usage, this means that when the firing solution requires that no deflection is used. Basically, point zero. Another term that we'll be using here is a mil. A mil is 360 degrees divided by 6,400. It is roughly 0.06 degrees. A mil is used because degrees in the 360 degree circle are actually too large for the corrections that we'll be using. A rad is 35 mils. This is the standard radius for one ring of a gun sight and is approximately 2 degrees. So in a 3-ring gun sight here, one radius is 35 mils, 2 rads is 70 mils, and 3 rads is 105 mils. We can imagine a situation where a fighter is approaching a bomber from the rear. Here, this is a straight line. There's no difference in the relative angles between the aircraft. And so this would be a point-blank firing solution. Now let's imagine a situation where the bomber is stationary and the target is moving. It is clear that to intercept the target with the bullets, the gun must be aimed out in front of the target to provide lead or a deflection ahead of the target. But let's imagine the opposite situation. Let us suppose that the bomber is moving at 200 miles an hour and the fighter is stationary. Then in this case, the forward direction of the bullets as it is carried along with the aircraft requires that you actually aim behind the attacking target because the bullets will be carried forward, and by the time they strike the airplane, they will be out in front of the original aiming point. This is very counterintuitive. That you would actually aim behind the target. In a situation where the target is attacking from 90 degrees, its motion in this direction is essentially zero. And so even though the fighter is coming straight at the airplane and is moving at 300 or 400 miles an hour, its motion in this direction is zero. And so the gunner must actually aim between the target and his tail to account for the forward speed of the bomber as its bullets are carried along. To represent this with a gun sight, we'll make the following demonstration. This is an attack from directly behind at the 6 o'clock position, and this would be the firing solution that one would see through the gun sight with no deflection required. However, if we have an attack from 90 degrees out, as mentioned, the gun must be aimed behind the target, and so therefore we use 3 rads of deflection. When the attack reduces to a 45 degree angle, then the rads required is reduced to 2. And at 22.5 degrees, the deflection required is only 1 rad. And at 11 3/4 degrees, the deflection comes down to 1/2 rad. The same holds true for frontal attacks. An attack from the 12 o'clock position is a point-blank solution requiring no deflection. However, at 45 degrees, the gun must be aimed back towards the tail, away from the nose, 2 rads. At 22.5 degrees, it only requires 1 rad. The 3-ring gun sight can also be used to measure range. For a typical single-engine fighter, at 600 yards out, it takes up about 1/2 of a rad. At 1,000 yards out, it takes out about 1/3 of a rad. It would be rare for an attacking fighter to stay in a straight line at any point during the attack. Even with head-on attacks with very high closure rates, which were very popular for the German Luftwaffe during World War II against our B-17 bombers in the early part of the war, any flight path that remains stable makes the target much easier to attack. Therefore, attacks generally occur in a pursuit curve, something like this. And as you can see, the angle is constantly changing. And this required the gunner to both change his estimation of range as well as his deflection during the entire part of the pursuit curve attack. There were disadvantages to using the metal or iron gun sights, whether 1 ring, 2 rings, or 3 rings. The first is that the head position is critical. If you cannot keep your head exactly in the right position, the ability to determine the deflection is severely impaired, and obviously that is very hard to do when you're swinging a gun around in combat. Secondly, there's the constant need to refocus. You have to focus on the gun sight, and then you have to focus out much further on the attacking aircraft. Finally, there seemed to be less accurate range measurement and less accurate deflection measurement using the ring sights. This led to the development of the optical gun sight, which broadcast an image onto a reflectorized piece of glass. This actually put the image out to infinity. And the advantages of an optical sight were that no matter what your head position was in, the image that you saw from the reticle was correct. And it made it much easier to estimate range and deflection because of that. Also, because the image was essentially broadcast out to infinity, there was no need to constantly refocus near and far, near and far. You only needed to look at the image that was being sent out and put that on the target. Variety of World War II optical gun sights. The first is the N3, which was very widely used in fighters throughout the early part of the war. And here you can see the reticle image here with a single ring. This is an N6 gun sight, which was used during in turrets during the war. And you can see here that it is also a single ring image projected. And finally, this is the N8, which is likewise used in turrets during the war. And you can see here that this is actually a 3-ring design. This is the K3 computing bomb sight used in the upper turret of the B-17 during the war. The K4 turret was an upside down version of this used in the ball turret. And we'll take you on a bit of a tour here before explaining the functions. These two boxes here are where rotary drive cables were connected to the turret, and that helped determine the elevation and the azimuth functions. As the turret turned and as the guns elevated, those rotary drive shafts work these mechanisms here to input elevation and azimuth information. Here is where the gunner would set the range, and we'll explain how that was done. This also used a rotary drive cable, and this was connected to a hand grip for the gunner in the upper turret, or to a foot pedal in the gunner in the ball turret. And with the hand grip mechanism, the gunner would rotate that, which would rotate another drive cable, which would adjust and for the range in the reticle. And we'll also show how that works. Finally, the other input here is the target dimension, or the width of the aircraft wingspan. And all this determined where the reticle was and how it was going to be displayed in the gun sight. The K3 Gunsight had to solve for multiple problems. It had to accurately determine the range of the attacking aircraft, and it had to make a prediction of where that aircraft was going to be. It had to do that in a lateral plane, or the azimuth prediction, and it had to do it in a vertical plane, or the elevation prediction. Ballistics were involved, as always in all gunsight functions and aerial gunnery, and there was a lateral ballistic deflection and a vertical ballistic deflection. And then finally, the K3 Gunsight had to combine all of these to come up with a solution. To explain the range function, the gunner's eye is here, the reticle is here, and the attacking fighter aircraft is here. This is the width of the fighter's wingspan, or target dimension, TD. This W here is the width of the reticle. The distance between the gunner's eye and the reticle is K, and the distance between the gunner's eye and the fighter aircraft is the range. It turns out that the ratio between the target dimension here and the width of the reticle here, K, is the same as the ratio between the range between the gunner's eye and the aircraft and the distance, K, between his eye and the reticle. Therefore, target dimension divided by W, or width of the reticle, is the same as the range divided by K, which is the distance between the gunner's eye and the reticle. TD divided by W equals R divided by K. Therefore, range can be solved for with the total dimension of the target times K divided by W. It is also important to note that the range of the target is inversely proportional to the time. In other words, the closer the target is to the bullet being fired, the shorter the time, and the further out the aircraft is, the longer it will take the bullet to strike the target. When you stop to think about it, the Norden bomb sight, with its many thousands of parts, basically used a moving platform and a stationary target to calculate the point at which the bomb should be released. Even when bombing a ship, this was only in 2 dimensions, and generally the bomber was aligned with the long axis of the ship going in one direction as opposed to across the bombardier's field of vision. Here, not only was the airplane moving, but the target is moving. And not only is the target moving in one direction, it's moving in all 3 directions. So the complexity of this device rivals the Norden bomb sight in being able to calculate how to fire a bullet accurately from a moving platform at a moving target in 3 dimensions. In terms of determining the lateral and vertical ballistic deflections, the ballistic effects chiefly are 2. One is gravity, how much the bullet will drop over its course of flight, and air resistance. The velocity of a 50 caliber bullet is well known, and basically knowing the time that it's going to be in flight helps determine how far it's going to drop due to gravity and how long it'll be slowed by air resistance. The Gunsight, with its many hundreds of gears and rotating shafts and cams, was able to solve for the ballistic deflection, and it was set internally to assume an airspeed for the bomber of 200 miles an hour, 50 caliber bullets, and an altitude of 15,000 feet. Here's where things get a little bit complicated. GA is gun azimuth and GE is gun elevation, or horizontal and vertical. As mentioned, both of the inputs for this are on the lower right of the gun sight and driven by rotary drive shafts, which provide GA and GE inputs. The gun sight uses rates of change of the azimuth and elevation. So the gun sight determines the azimuth rate, how fast the turret is rotating, and the elevation rate, how fast the guns are moving up or down. Using the time that it knows because of the range, which we said was inversely related to time, the azimuth rate times the time gives a lateral prediction deflection, and the elevation rate times time gives a vertical prediction deflection. In other words, there's the present position of the target and its future position. Just as the Northern bomb sight used time of fall and ground speed to determine the bomb release point, the Gunsight uses azimuth rate and elevation rate along with time to determine where the fighter is going to be from its present position, giving a future position or a deflection. The Northern bomb sight determined ground speed by synchronization with the target. The Gunsight also has an internal motor which helps interpret the rate of elevation or azimuth change as input by the rotary drive cables. Finally, the Gunsight had to combine all of these predictions. It took the lateral prediction deflection, which was determined by the time times the azimuth rate change, and the lateral ballistic deflection, and came up with the total lateral deflection. Similarly, it took the vertical prediction deflection, which was obtained by getting the vertical rate times the time, and the vertical ballistic deflection, and when these were added together, that gave the total vertical deflection. It was able to combine all of these with the range to come up with the exact aiming point for the gunner. Here we can see the reticle, and the vertical lines will be lined up with the wingspan of the attacking aircraft. The first thing we're going to do here is adjust for the target dimension, and that's hard to see in this dark window here, but a general rule of thumb is that for single-engine fighters, you set that at about 35 feet. And you can see that narrowed the reticles up there. The range right now is at 1,000, and you'll see that as we decrease that, the reticles start to move apart. It's down to 800 feet. And as the fighter gets closer and closer and closer and closer, the range gets shorter and shorter. The reticles spread out to account for the increasing size of the image of the aircraft and its wingspan. And finally, we'll demonstrate an input into the gun elevation terminal, and you can see here that the reticle goes up, tracking the enemy aircraft, and then comes back down to normal. And you would track that all the way around, and as you track it, the rate of change of the elevation will give the vertical prediction deflection, and likewise for the horizontal deflection.